Wire antennas, effective length, area, series on antennas and wave propagation, lecture number 1.16. Antennas in general require to fulfill multiple requirements when they are used in wireless communication systems. Hence, they require several parameters indicating their performance in different aspects of their functioning. In the present session, we consider one or two important performance indicators of antennas. One is effective length. This parameter is more relevant to wire antennas. It is useful to describe the antenna both in transmitting mode as well as receiving mode. Another important parameter we consider here is effective area. It is more relevant to aperture antennas. It describes the performance of antenna while it is functioning in receiving mode. In addition to these two, we also consider some more aspects pertaining to antennas functioning like polarization. A small list of performance indicators of antennas are given here. Directivity, gain, power gain, radiation pattern, effective length, area. Now we are going to discuss about these two. Polarization. This also we consider in the present session. Impedance, bandwidth, these are all aspects. And these are some of the aspects which indicate the performance of antenna. This is not a complete list. Now we consider effective length for discussion and understanding. It is relevant to wire antennas. Effective length is relevant to wire antennas. It is defined with respect to antenna either in a transmitting mode or receiving mode. So effective length can be defined for an antenna. It doesn't matter whether it is transmitting antenna or receiving antenna. It indicates the effectiveness of the antenna not only as a radiator but also as collector of EM energy, electromagnetic energy. It can be related to directivity, a transmitting mode parameter. Conceptually, it is near to effective area. Notice directivity is a transmitting mode parameter, whereas effective area is receiving mode parameter. Whereas effective length is okay equally for both modes of operation. It is equal to the product of physical height of the antenna with the normalized average current. Normalized average current. Effective length, also known as effective height, both are same. Effective length, effective height, both are same, is exclusively relevant to describing the performance of linear tower type antennas, linear wire tower type antennas. As already mentioned, effective length is relevant both to transmitting as well as receiving modes of the antenna. It can be defined, it is defined actually for transmitting antenna, it is defined for receiving antenna. That is okay. Here he is mentioning another aspect. Effective length is relevant both to transmitting as well as receiving mode. Of course, for wire antennas, Now a definition, formal definition. Effective length of a transmitting linear antenna with a physical length of L located at the origin along Z axis carrying a current distribution I of Z having a maximum value of I max is defined as a physical length of an equivalent linear antenna having uniform current distribution I max and radiating a field equal to that of actual antenna in the normal direction. Normal means perpendicular. Mathematically, the statement implies L effective is 1 by I max integral minus L by 2 to L by 2 I of Z dz. This definition is when the antenna is in transmitting mode. I is current distribution along the length of the wire antenna. L is length of the actual antenna, physical length. I max, maximum value of current distribution. So this is the definition of effective length. Here the definition is illustrated. L is a physical length, capital L. L effective is effective length, this one. I of Z indicates current distribution. Here you can see it is varying in a sinusoidal manner. I of 0 means here. What is I? Now substituting expression for I of Z in the expression for L effective length, one can determine its value. Notice here E is considered normal to the wire antenna. It is normal. This is the length normal to the length of the antenna. Effective length can also be defined for a receiving antenna. As already mentioned, it is relevant, it is useful for both modes of the antennas. For transmitting mode, it is already defined. For receiving mode, for a receiving antenna, it is defined here. It is the negative of ratio of open circuit voltage VOC at the antenna terminals to the uniform incident field E parallel to the antenna. L effective receiving mode in receiving mode is equal to VOC by E with a negative sign. It can be shown effective length of an antenna when transmitting is the same as that when it is used for receiving. It can also be shown that the effective height is equal to product of physical height of the antenna with normalized average current. Before going further, some explanation regarding effective length of receiving antenna. Let us suppose a wave is coming and electric vector is vertical. Here you placed a wire antenna like this. E is parallel to the length of the wire. When the wave falls over the wire, certain amount of voltage gets induced across the wire. That voltage is VOC. VOC by E, electric field intensity in the incident wave, is that ratio is effective length. This is as far as antenna in receiving mode is concerned. When antenna is in transmitting mode, how effective length is defined? This is actual antenna. The length is L. It has certain current distribution. So it is radiating, giving certain field intensity E. Now, effective length of this antenna, actual antenna, is physical length is L. Effective length of this antenna is length of another antenna. This length, let us call it effective length of this antenna having a uniform current distribution like this equal to I max. Here let us say maximum current is I max. Uniform current distribution equal to I max, and radiating same field intensity. The field intensity which is the same as given by the actual antenna. The length of this antenna is effective length of the actual antenna. This is definition. As per definition, it can be shown effective length is equal to product of physical height of the antenna with normalized average current. Now we move to another important specification of antennas: areas, effective area. In addition to effective area, there are some more areas when the antenna is in receiving mode. Of course, out of all this, effective area is more significant, more important. We consider effective area and other areas too here. Areas of antennas are defined with respect to antenna in receiving mode. These are more relevant to aperture antennas. Effective area can be related to directivity, a transmitting mode parameter. In the definition, we come across available, term available. It implies maximum power that can be drawn. Implementation of maximum power transfer theorem. Wave at receiver can be approximated to a plane wave at its origin. Transmitting antenna is far away from receiver. Away, it is away. So what he says is wave at a receiver can be approximated to a plane wave as its origin. Transmitting antenna is far away from the receiver. Notice here is a transmitting antenna. It emits wave, but this wave is not a plane wave. But by the time it reaches the receiving antenna, when the distance between transmitting antenna and receiving antenna is huge, this wave at the receiving antenna can be considered as a plane wave. Areas of antennas are defined here: effective area, scattering area, loss area, capture area. These are the areas. Out of these four, effective area has certain special significance. It is by definition power available at antenna terminals to power density of the incident wave. Scattering area AS is power re-radiated back by antenna to power density of the incident wave. Loss area AL by definition is power dissipated in conductor dielectric losses to power density of the incident wave. Capture area AC is equal to power captured by antenna to power density of the incident wave. We go somewhat deep into the definitions given here in the next slide by considering some illustrations. Now, here is an antenna, receiving antenna. Wave is coming from a large distance, so it is a plane wave. In a plane wave, power density is given by E square by 2 eta. If a transmitting antenna is a dipole, the wave emitted by it is a cylindrical wave. If it is a horn antenna, wave emitted by it is a spherical wave. So wave emitted by the transmitting antenna, it depends upon the antenna, but the wave that reaches the receiving antenna is nearly plane wave. Whatever may be the wave emitted by transmitting antenna, when it is at the receiving antenna, it is a plane wave provided the distance between transmitting and receiving antennas is large. In case of plane wave, power density is given by E square by 2 eta. Capture area is AC. When capture area is AC, captured power becomes ACS. So PC becomes ACS. That is A. Now B. Out of this captured power by the antenna, some get scattered back, some get consumed as losses. Remaining is available at the output terminals of the receiving antenna for further processing. So this diagram, this illustration gives complete or total picture of the interaction that happens between receiving wave and the receiving antenna. Now some explanation, description to enhance the understanding of areas of antenna. The power of the wave incident and the proportions into which it is divided are conveniently described by scattering area, loss area, effective area, and capture area. So this is the significance of these areas. Scattering area of a receiving antenna is defined as a ratio of scattered power to incident power density. It is equivalent area of the antenna which when multiplied by incident power density is equal to scattered or re-radiated power. Loss area of a receiving antenna is defined as ratio of power dissipated in conduction dielectric losses to incident power density. In other words, it is an equivalent area of the antenna which when multiplied by the incident power density gives power dissipated as heat in RL, which represents conduction dielectric losses. Effective aperture, effective area, as already mentioned, is most important out of the antenna areas. Effective area, its symbol is AE, of a receiving antenna is the equivalent area which when multiplied by incident power density gives the power available at the antenna terminals. To be precise, the effective area of a receiving antenna in a given direction can be defined as ratio of available power. Available means maximum that is possible to be extracted from the antenna. Here maximum power transfer theorem is relevant. It is the ratio of available power at the terminals of a receiving antenna to the power density of the incident plane wave on the antenna from that direction, the wave being polarization matched to the antenna. Notice the wave at the receiving antenna is a plane wave. This fact is being stressed again and again. The importance of this particular observation is with this we will be able to find density, power density in the incident wave. Power density is actually E cross H. But as it is plane wave, it is equal to E square by eta. For this reason, it is being stressed that it is a plane wave. In the definition, it is also being told that incident wave is polarization matched with the receiving antenna. This is also an important aspect. When mismatch is there between wave and receiving antenna, then antenna may not be able to receive the wave, incoming wave, to its fullest capacity. Mathematically, AE is equal to available power from the antenna terminals, WR, by power density of the incident wave, S. Capture area. Capture area of a receiving antenna is defined as ratio of power intercepted by the antenna to the incident power density. So it is an equivalent area which when multiplied by the incident power density leads to the total power intercepted, captured or collected by the antenna. In general, the total capture area is a sum of effective area, scattering area and loss area. AC is equal to AE plus AS plus AL. Some important points regarding effective area. The effective aperture is an important property of the antenna. In receiving mode, it depends upon several factors like physical area, orientation, surface characteristics, polarization, etc. On the other hand, directivity is a key parameter describing antenna performance in transmitting mode. For any antenna, these two are related. That relation is given by AE is equal to lambda square by 4 pi multiplied by D. So this particular slide is meant for connecting effective area with directivity. A few points regarding polarization. The polarization of the antenna is defined with respect to its transmitting mode. It is in a given direction defined as polarization of the wave transmitted emitted by an antenna. Here is an antenna. It can be used either in transmitting mode or receiving mode, but as far as its polarization is concerned, it is defined when it is acting in transmitting mode. Polarization of this particular antenna is polarization of the wave it emits. Polarization pattern represents polarization characteristics of the wave the antenna emits, and it is defined as the spatial distribution of the polarization of a field vector radiated by the antenna taken over its radiation sphere. At each point over the sphere, the polarization is usually resolved into a pair of orthogonal components, one along polar angle theta and the other along azimuth angle phi directions. These components are called copolarization and cross-polarization. These terms we encounter in wireless communication systems, copolarization and cross-polarization. Primary polarization and cross-polarization. An antenna may have two orthogonal linear polarizations. Desired polarization is called primary or copolarization, and other polarization is called undesired one is called cross polarization. But by proper design of the antenna and our proper selection of coordinate system, the antenna can be made to have only one polarization, either theta polarization or phi polarization. Polarization in theta direction or phi direction. The plane wherein the electric field varies is also known as polarization plane. These are some of the terms we encounter frequently while studying antennas. Some more points regarding polarization's importance. For efficient reception, the polarization of the receiving antenna and incoming wave should be the same. There should be a polarization match between receiving antenna and the incoming wave. Both must have same polarizations, preferably. If the incoming is elliptically polarized, the receiving antenna can be elliptically polarized with the sense of rotation same as that of incoming wave and major axis of both polarization ellipses pointing in the same direction, preferably. In such case, maximum signal strength can be extracted from the receiving antenna. Antenna is able to give optimum performance. Two other situations are being mentioned here. In these two situations, the performance of the antenna is suboptimum. First one is optimum, second one is suboptimum. Optimum exists. Optimum performance exists when polarizations match perfectly. When matching is not perfect, then suboptimum performance. So when incoming wave is elliptically polarized, linearly polarized with its E vector aligned to major axis of the polarization ellipse of incoming wave. This type of antenna can also be used, but as already mentioned, it is suboptimum performance. Circularly polarized antenna with a sense of rotation same as that of incoming wave also can be used, but it gives suboptimum performance. If the incoming is linearly polarized, the receiving antenna can be linearly polarized with its E vector parallel to that of the incoming wave. This is optimum performance situation. Remaining two are suboptimal. Circularly polarized with any sense of rotation or elliptically polarized with any sense of rotation with its major axis aligned to E vector of the incoming wave preferably. If the incoming is circularly polarized, the receiving antenna can be circularly polarized with the sense of rotation same as that of the coming wave. It gives optimum performance. Remaining two gives suboptimal. Linearly polarized antenna with E vector in any direction. Elliptically polarized antenna with the sense of rotation same as that of the incoming wave. Notice before going further that sense of rotation is also an important aspect. Let us suppose incoming wave is circularly polarized, receiving antenna is also circularly polarized. So polarization is the same, but it is not sufficient. One more factor is there which has to be tallied, which has to be agreed upon by both wave and that is sense. If the wave is clockwise and antenna is anti-clockwise, or antenna is clockwise and wave is anti-clockwise, then signal cannot be received by the antenna. Zero signal appears at the output terminals of the antenna. With this, we come to an end of the session. In the present session, effective length, effective area, and other areas are described, defined, connected. Hope this session is useful to you. We meet again soon in another session with a new topic.